let an, or some sequence, be 2n squared plus 4n minus 3 over n squared minus 4 ln n for positive integer n. Because this is a sequence, remember the domain of a sequence, the natural domain, is the positive integers, because for the first term n is 1, second term n is 2, third term n is 3, and so on. We need to find the limit as n approaches infinity of an, the nth term, as in the actual limit of the terms in the sequence. We're not talking about a series here, we're talking about a sequence. So the first thing you probably should be doing, or the first thing you definitely should be doing, is looking at those powers. Okay, so a lot of the things you've done with functions to find these limits in the past, you can do exactly the same thing here. So if you look at those powers on the top and the bottom, the highest power of n is n squared. So the first thing we're going to do is multiply top and bottom by 1 over n squared. So we're going to say the lim as n approaches infinity of an equals the lim as n approaches infinity, and we're going to divide every term, top and bottom, by n squared. So we're multiplying by 1 over n squared over 1 over n squared. If we do it to top and bottom, we're just multiplying by 1, so we're not changing the actual value of that fraction, the value of the sequence. So that is going to be 2n squared over n squared plus 4n over n squared minus 3 over n squared over n squared over n squared minus 4 ln n over n squared. So the limit of all of that, I think we need a bracket. Okay, so that will, most of this will tidy up, and there's probably only going to be one bit that we're going to have to do some more work on. So now this equals the lim as n approaches infinity of, well, 2n squared over n squared is just 2, so 2 plus 4n over n squared is 4 over n, 4 over n, minus 3 over n squared is okay, over, well, n squared over n squared is 1, and this is minus 4 ln n over n squared, right? So now, if you look at that, we can do a bit of this in our heads. We don't need to write everything down. So if you look at all these limits, remember, you can say, well, the limit of the quotient is the quotient of the limit. So we can do the limit of the top and the limit of the bottom separately, and then we can say the limit of the sums is the sum of the limits. So we can do all of these limits separate, 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 right? Because all of these, apart from this one, they all look okay. So this one here, the limit as n approaches infinity of 2 is just 2. For the 4 over n term, the limit as n approaches infinity of 4 over n, you can take the 4 out, and that's 4 times the limit as n approaches infinity of 1 over n, so this is just 0. This one can be minus 3 times the limit as n approaches infinity of 1 over n squared. It's 3 times 0, it's just 0. The limit as n approaches infinity of 1 is just 1, and this one is going to need some more work, but what we can do is pull the minus 4 out. So now this equals 2 plus 0 minus 0 minus 0 over 1 minus 4 times the lim as n approaches infinity of ln n over n squared. So now we're going to have to do some work to find this bit. But once we've got that, we will be able to finish the limit. Okay, so it's not an easy one to find, ln n over n squared. So what we're going to do, we're going to look to see if we can squeeze it. So can we use a squeeze theorem? So firstly, we know that n is always greater than or equal to 1. So if you have a situation like this, it might be good just to think about what ln n looks like. So say if y equals ln x. I'll bring a function back because plotting an n means that you have to draw dots and not a line, and it's just a bit more difficult. But I can put dots over the top. So if y equaled ln x, then x would equal e to the y, which is easier to draw. So we're going to draw e to the x, so we need y-axis and then the x-axis, and we know we have an asymptote is the x-axis. It goes through the point 0, 1, and that is y equals e to the x, and then we can draw the inverse function. So if we want to draw ln x, which is the inverse function, well, we need to reflect it in y equals x. And remember, any point on the function, we can swap the coordinates around, and that will be a point on the inverse function. So if this passes through 0, 1, the inverse function is going to pass through 1, 0. Okay, so that's a good point. And then everything else, it just gets reflected. Also, don't forget about asymptotes. If the asymptote is the x-axis on the function, then it'll be the y-axis on the inverse function. So it's going to come through like that, and then just reflect in y equals x. We could draw y equals x if you wanted. Looks like that. So this is the graph of y equals ln x. So if we wanted to draw ln n for n greater than or equal to 1, well, it starts, remember, the first n would be 1, and then it would be 2, and then it would be 3 and 4. So the dots are, it's the sequence ln n, right? Right, so just looking at this, for n greater than or equal to 1, you can see that ln n here, which is these dots, are always underneath the graph of n, or y equals x is the line, so y equals n are the dots when it's just plotted as integer values of x, or positive integer values of x. So ln n is always less than n, and also if you look at it, because we have this domain of a positive integer numbers, it actually never goes below 0 either. Greater than or equal to 0, right? So this is now something that we can use to squeeze. So if we have this, so 0 ln n, like that, for positive integer n, that means if we look at if you think of what we're aiming at ln n over n squared. So if we divide everything by n squared, which is positive, so it won't flip the inequality, well, 0 over n squared is just 0. ln n over n squared is ln n over n squared. N over n squared is 1 over n. So that is true for all positive integer n. So now we can get the limits. So the lim as n approaches infinity of 0 is less than or equal to the lim as n approaches infinity of ln n over n squared, which is less than the lim as n approaches infinity of 1 over n. Well, we know that the left hand side is definitely 0, the right hand side is 0, we see it all the time. So now we can say, well, this is definitely 0, so lim as n approaches infinity of ln n over n squared equals 0, and the reason is the squeeze theorem. We got it squeezed in between two limits where we knew one was definitely bigger than it and the other one was, well, it could have been equal, but it was definitely smaller or equal to, or less than or equal to. Once we got it squeezed between those two and we showed that those two limits were the same, the outer limits, then it proves that the middle limit is exactly the same value. So now, just to finish it off, the lim as n approaches infinity of the sequence an, well, it equals our 2 plus 0 was just 2 over, it was 1 minus 4 times, remember the limit as n approaches infinity of ln n over n squared, so 4 times 0, which is just 2 over 1 equals 2. Okay, so that is a bit tricky, but it's good practice of all the things we've already used for functions. And it is, when you get these natural logs, it is always a good place to start. You're going to have to get very good at doing things like this and getting things you can squeeze, or getting things you can use the comparison test on. You will become very well practiced in this, well, you absolutely need to.